Welcome back. This is example 4 from 1 to day 6, 3.1, Lagrange polynomials. Where we want to consider the function of the values of the function f of x equal to net log of x, accurate to the places given. In other words, there's 4 significant digits here for the value of f of x and net log of x here. And we want to use this data with Neville's method to approximate the value of the function and evaluate it at 2.1. So we want to evaluate the natural log at 2.1. And then, so you can see that the data given, I recreated in this table in GeoGebra, so the spreadsheet for GeoGebra. So I go ahead and I plug it in. We're given the data 0, 1, and 2. These are the 3 points that we're using to do the interpolation around. The xi values we're given are 2, 2.2, and 2.3. And what we're looking for is the value between 2 and 2.2, that 2.1. So the xi values, the natural log of xi, so it's the natural log of this value of 2 is 0.6431, 0.7885, and 0.8329. Okay. The value that we're looking to interpolate is here at 2.1. And this value here is f of x, or I should say f of 2.1. You might say quote unquote, and there it is. So I'm taking the natural log of value. And so if I do that, I get that it's, oh, I forgot to put that in parentheses, I mean in quotations. The spreadsheet in GeoGebra will evaluate it if you don't put it in parentheses. So that's f of x. So this is the actual value, and that's what we'll use later in our computations. Okay, and so I've set the Neville's method. So I'm going to copy here my 3 I values, and I'm going to paste those down there. Okay, and then I also copied the xi values here. And the reason I'm doing that is just so everything's kind of in the same table format that Neville's method is familiar with. And if you look at other examples online or other places, you'll see that as well. All right, so these values, this is the difference between x and xi. This is where I'm evaluating it at. And so I'm going to take the differdifference of this value of this value, E1 or E2, and subtract it from this value. So this is the difference between 2.1 and 2, 2.2, 2.1 and 2.2, and 2.1 and 2.3. So this is these values. Okay, now here gets the start of Neville's method. And these are the QIs from Lagrange's theorem about interpolation. So here we have the QI0. And so you can think of these as, the notation is a little bit tricky here, but the idea here is that the second number kind of indicates the power or the degree of the polynomial. So this is the constant value because the exponent on, let's say, x would be 0 here. So these would be all the constant terms. In other words, these are the values of the function given that we're going to be utilizing in our interpolation. Okay, so our next job is to then utilize these values to construct the first degree polynomial, interpolation polynomial, and then the second degree interpolation polynomial. So we're going to go ahead and do that now. So we're going to set this equal to, and so in this value, we're kind of creating a weighted difference. So we're going to take the value here. We're going to take this value here. Let's see, and look at this one right here. So C8. We're going to multiply that by the value of the linear function or the constant function here. So that'll be at D9. And then we're going to subtract from that the value of C9 times D8. And so you can kind of see it kind of makes this X pattern. So it's this times this minus this times this. We're going to put in that parenthesis, and then we're going to divide that by the difference in the X values. So that'll be B9 minus B8. Okay. And so if we perform 4 digits, so it should be 0.7408. And if we're using 4-digit arithmetic, that actually simplifies to 7.4.10. But well, that's a different animal to tackle. So let's go ahead and continue with this. So we're going to go here. We're going to take, doing the same thing. We're going to look at C9. We're going to multiply that by D10. And then from that, we're going to subtract C10 times D9. And then from that, we're going to subtract D10 from the result you would expect, which Let's look at that again. I think I was talking and then it clicked off and then I was confused about what happened there. So we can just pull this down, but to verify that we're getting the same result, this is the same thing as that should be D9 times, not D9, sorry, C9 times D10 minus D10 times, not D10, sorry, C10 times. I'm looking at the wrong one as I'm saying it, D9. And then this would be the difference of B10 minus B9. Okay. And so you see that that gets the same result. So when you pull this down, it shows that it gets the same result. Okay, and then finally, then we're going to compute the quadratic one. And so this one's a little bit different because we're going to be looking at, we're going to be using these data points to make the difference. And so this is in right equal to, GeoGebra actually is good enough to know that you can hit equals, or if you just put in the parentheses, it knows it's a calculation. The only bad thing is that like in Excel, you could click over and you can move the cursor around and it would highlight the cell. Here you have to input the cell names. Okay, should have mentioned that earlier. But anyway, we're going to go from here. We're going to take C9, and that's going to be multiplied by, oh, I clicked out. I clicked out of the thing. It caused a momentary glitch. Sorry about that. So we're going to take, let's see, what do we have? We have C9. Okay, we have, let's see, we have C8 times. So we're going here to this value. So it'll be E10 minus, we're going to go with this value. So C10 times this value, which is E9, E9. And then we're going to divide that by B10 minus B8. Okay, and so then our value is 0.719. Okay, and if you notice here, the difference between these two is identical up to that fourth digit. So we're going to take the absolute value of F2 minus 0.7419. And so we get that this error is accurate out to the 4 digits of accuracy. Okay, so that gives you a really good estimation then of this problem using the Neville method. So I hope that was helpful. The trick on these is just being careful that when as you're going out, that you're using this difference with the truncating sequence out here. But it still follows that back and forth pattern, that kind of X value. And then the other thing is when you're doing the denominator, you want to subtract the value that you're at, kind of like the level that you're at with the first term here. If that's what you're estimating. Okay, all right, I think that was helpful, or I hope that was helpful, and I'll see you in the next video.